Hi everyone, my name is Nazanin Faragpur and I'm a PhD student at University of California, Los Angeles. Today I'll be presenting our work in progress paper on FPGA-based near data processing platform selection using fast performance modeling. In recent years, industry-leading companies such as Amazon and Microsoft are shifting towards incorporating FPGAs into their servers and using them to accelerate a broad class of applications. These examples, as well as Intel acquiring Altera a few years ago, has shown that FPGAs are becoming a standard components of the cloud infrastructure. Due to this trend, there are various FPGA-based acceleration platforms developed in recent years that could be categorized in 4 groups. FPGAs could either be used as I/O-attached accelerators or closely integrated with CPU as an on-chip coprocessor. For a more data-centric approach, FPGAs could be moved closer to the data medium and be used as near memory or near storage accelerators. Since a typical server workload consists of a broad spectrum of application, we expect to see in near future server racks equipped with one or more types of these FPGA resources to match that workload intensity. So it's crucial to have a method of mapping applications to the most suitable platform. So in this work, we first take a look at 18 widely used applications from 5 domains of search, security, database, vision, and finance, and analyze their qualitative and quantitative attributes. Then, we present a first-order quantitative performance model based on some of these attributes to help us identify the potential performance bottleneck of each application that could help guide the platform selection. And we will try to answer the question that could all applications dealing with in-memory or in storage datasets benefit from near data processing or not? These are the 18 benchmarks that we looked at. The FPGA kernels are mostly from the Xilinx VTIS library, plus a few of our own benchmarks. We looked at application-specific attributes that are not related to the FPGA kernel itself, but rather more related to the use case of the application. And we also looked at kernel-specific attributes that could be collected from the kernel itself and its high-level synthesis. 2 application-specific attributes are memory capacity and working set size. For instance, a query processing engine which receives consecutive queries that target dozens of SQL tables, but for each query response, it only works on 1 table or 2. We would consider the whole database size as memory capacity and requested tables for each query as working set size. So together, these 2 create a trade-off in platform selection. Another performance attribute is input-output data flow that shows whether, for instance, input data resides in memory or in storage level, or the output generated will be stored, transferred over the network, or used by other applications. Another criteria is data reduction ratio. One of the main motivations of the near data processing is reducing the data movement, so if an application has an output size similar to input size, it will hinder the benefits of near data processing. This figure shows the reduction ratio of our applications. We see that applications in search domain has high reduction ratio. Also, in database domain, some query processing kernels such as combine and partition have reduction ratio of 1, but it's fair to say they are usually used in conjunction with other kernels such as select or aggregate that will reduce the output size significantly. There are useful informations that could be collected from the FPGA kernel and its high-level synthesis. For instance, knowing the kernel operating frequency, initiation interval, and input-output bit width would help us estimate what is the peak data processing bandwidth that the kernel could reach and whether it could saturate the bandwidth of the attached memory. In this figure, we see the peak bandwidth achievable by each kernel in our benchmark. Other attributes are the access pattern to attached memory, number of passes over the initial input data, and the intermediate data size that each could have effect on the platform selection. Now, using the discussed attributes, we present a first-order performance model to guide our platform selection. We assume data initially resides in storage, and kernels use Xilinx AXI stream interface to communicate with the attached memory level, and they all have on-chip scratchpad memories, and they use double buffering. Based on these assumptions, the load, compute, and store phase of each application could be done concurrently, and knowing this fact, one of these three phases would be the limiting factor or the bottleneck of the specific platform for each application. We also add an initial delay factor to take into account an initial data file movement to the attached memory level. Now, due to timing constraint, I won't be going through every equation in detail, but overall, we present a formula for each of these compute, load, and store for each of these acceleration platforms based on the attributes that we discussed. For near storage and PCI attached FPGA, we assume a direct connection to storage, and therefore there is no initial delay. We present the load and store formulas based on the attributes discussed previously as shown here. Now, for near memory and on-chip accelerators, there is an initial delay of loading to main memory, as we assume the data initially resides in storage. But similar to near storage and PCI attached, we present a load and store formula for these platforms as well. Based on any specific system configuration and bandwidth information, we could estimate throughput of our applications under this model. Our analysis shows that applications with no data reuse and high reduction ratio maps well to near storage accelerators. For compute bound applications with low peak bandwidth and reduction ratio, it's better to stream data into a more powerful PCIe attached accelerator. And for communication bound applications, the throughput is ultimately bound by near storage acceleration performance, so it's better to just leave them near storage. And partition hash join benefits from near memory acceleration due to multiple reuse of the initial data in this specific application. We extended the cycle-accurate parity simulator to model the 4 acceleration platform and their attached memory modules. We converted 6 of our applications into simulator-compatible versions and plugged in their parameters. The table here shows the best performing platform for each benchmark according to our model versus the simulation result. 4 out of 6 applications have a similar selection, but we also realized that the simulation shows the performance gap between on-chip near memory and PCIe attached accelerators are much smaller than what the model suggests. And we realized that many of the applications such as gem and swaption here consist of consecutive accelerator kernel calls, and each accelerator call works on a part of the input data, so the T-init, or that initial data movement, is actually partially concealed by the kernel execution. So we decided that for applications with multiple kernel calls, we could actually include T-init as part of the T-load for a more fair comparison. So in conclusion, our first-order performance model gives a quick analysis on the performance bottleneck of an application based on its attributes. And in future work, we are planning to validate more benchmarks based on our simulation system. And currently, we only looked at kernels individually, but they could be actually connected in a modular fashion with a stream interface, so that could be studied more. And we also understand that values such as intermediate data size, reduction ratio, and initiation interval could be input dependent for some applications, such as Viola-Jones face detection or swaption. And this could hinder the accuracy of the model. So we are planning to address these limitations in the future work. Thank you for listening. And if you have any questions, you can reach me at my UCLA email. Thank you.